Hi everyone, welcome to this video series on advanced tokenization algorithms that are typically used by BERT and transformer models. The advanced text tokenizers like Byte Pair Encoding and word piece, they actually play quite a significant role in modern natural language processing tasks, particularly BERT and transformers. These tokenization methods go beyond the traditional or classical word-based, approaches. For example, the tokenizers from NLTK or tokenizers that we see in SPACY and GenSim packages. BPE and WordPiece offer, quite flexible and adaptive tokenization methods, and thereby it enables the variable length input sequences handling, and also they allow the models to handle out of vocabulary words or rare words. This is crucial for models like BERT and transformers, because these models, BERT and transformer, they rely on pre-trained embeddings or MLM language modeling, and hence we need the advanced tokenizations like byte pair encoding. In addition to this, these advanced tokenizers also capture rich morphological variations, and hence it makes them quite useful in representing the languages that are little complex and intricate in linguistic structures. This is typically the taxonomy of the tokenizers that we typically hear about and we use. The classical methods like white space or punctuation, but in this video I'm going to talk about the byte pair encoding. In the next video I'll talk about word piece or sentence piece as well. We know what is tokenization, which is simply breaking down a text to a smaller unit. And why we need to tokenize? The purpose is to convert the unstructured textual data into a structured format or numeric format. For example, here, let's say the given text, and we can break the given text into a units of words, for example, and each word we can represent using a vector representation. Some of the key points on tokenization. This is quite fundamental. In fact, the first step of pre-processing, and it is characterized by a variety of methods for converting the input text into a smaller tokens or smaller units, and they are used based on words or subword formation. Byte pair encoding is a compression technique used in the text, but this was improvised or improved to suit natural language processing tasks by OpenAI and various other BERT and transformer models. I've listed a few of them here, but the list is much longer than what you see here. The byte pair encoding is a compression technique that I mentioned earlier, and especially it is used in the natural language processing, and the basis is subword tokenization. The concept of desired vocabulary size, BPE takes the input sentences or corpus, and then from the corpus it generates the most frequently occurring pair of words or group of letters or characters till the desired vocabulary size is reached. For just like a simple example or illustrating, let's say the corpus consists of these words. What we're going to do is we'll convert or we extract individual alphabets from these words and we sort them. For example, here B, G, H, and P. So this is my initial tokens. In real world, the vocabulary is always be all the ASCII characters plus some Unicode characters as well. Now, if you present some word which is or some letter which is not part of the training set, that will be converted to unknown token. Let's say this is our corpus and the word hug appears 10 times in the corpus. The word bun appears four times in the corpus. How do we train the tokenizer? We are going to split each word into individual alphabets. For example, hug split into H, U, G, and this is the frequency. And similarly, bun, B-U-N, is split into alphabets. Now, what we're going to do is we'll find out the most frequent pair of alphabets. For example, here H and U is present in HUG, and H and U is present here too. So total number of times H and U pair is appearing in the corpus is 15 times. But if you look at U and G is appearing here, U and G 10 times, U and G 5 times, so 10 plus 5, 15. And here is U and G again, that's 5 times, that's 20 times. So that means U and G is the most frequently occurring pair of alphabets in this corpus. So what we're going to do, we are going to merge. So this is our first merge. We found the most common pair of alphabets. So we add this most common pair of alphabets in our initial vocabulary set. We also transform the corpus to combine U and G with one token called UG here. Next again, we continue here. Let's say HG and then UG appears 15 times. U and N appears 16 times. So now, in this case, U and N or UN would be the most frequent pair of characters. So now we're going to add UN to the vocabulary, and similarly, we're going to convert or transform the corpus. Wherever U and N was split, we combine them into one token. So this process is going to continue all the way till you have reached the vocabulary size. For example, here the third iteration, HUG, and then HUG is the most frequent, for example, then HUG will be added to the vocabulary, and also we transform for example, this is the corpus where it was HUG separate. Now, because HUG is like one token, we make it like one token here. So this word now is consisting of two tokens, HUG and S. This is pretty much what happens in the byte pair encoding. Now let's say the training of the tokenizer recognizes UG, UN, and HUG as token, and you present the new word, let's say BUG. In this case, BUG will be tokenized as B and UG. MUG, on the other hand, will be tokenized with just a second. Yeah, so MUG will be tokenized. UG is understood. M is not understood, so it will be replaced with unknown. Similarly, THUG, HUG is understood, so it will be converted to this token. T is not understood, so this will be an unknown token. Now, transformer models, which we actually use BPE, quite a long list of BERT and transformer models. I've listed a few of them. Now, most of these BERT and transformer model, they use the fundamental principle of BPE, but there are some variations as well. For example, BERT and GPT and Robata and the cross-language or cross-lingual language model also uses the BERT byte pair encoding. T5, Albert, Distilbert, and Ernie, they are also using byte pair encoding with some variation here and there. So what's the advantage of BPE? Definitely one of the major advantages is ability to handle out of vocabulary word or morphological variations because of this subword formation. It is also language agnostic because again the reason is it is based on subword formation. Because of the subword formation, the BPE models can handle rare words also. In effect, you're going to get much better generalization by using a tokenizer which is based on byte pair encoding. Along with the advantages, there are some limitations of BPE as well. As you can see here, since this process is very iterative and finding out the subword in each of the iteration can lead to significant load in terms of computation. Vocabulary size can also be very large if the corpus or input data is very large. Because of subword, you could be also losing meaningful information or linguistic interpretation because of the subword. Now, that was the conceptual walkthrough or the theory behind the byte pair encoding. I'm going to show you a toy example using a Hugging Face library, walk you through an illustration as to how byte pair encoding actually works. Here is the little illustration of how byte pair encoding is actually accomplished. This is just illustrative example, not an optimized one. I'm going to be using Hugging Face transformer library and the auto tokenizer model. Um, Now, the little corpus here, the toy corpus, and the auto tokenizer that I'm using in this code is a GPT-2. You could use any other language model, let's say BERT or Alberta or Distilbert. Almost all of them work on the similar principles of byte pair encoding. Let's take the corpus and we find out the frequency of the words. Essentially, in this corpus, we are trying to find out the frequency. So this appears 3 times, and you see this kind of a weird looking alphabet, which means there is a space before is. Similarly, here also, there is a space before the, and there is a space before hugging. So this is how the tokenizer from the transformer library actually works. And this little character that you see is to identify or to indicate that there is a space, a blank space. Now, next, what we're going to do is to find out the initial vocabulary, which is individual letters or alphabet from the corpus. This little piece of code is running through your corpus and splitting the words, and then each of the word we is split into characters, and we build a unique set of alphabets here. We're also going to add something like a beginning of a vocabulary. This is how GPT-2 actually works. So we need to add exactly in the same way, just add the beginning of the vocabulary set. So now you see here, added in the beginning. Next up, what we're going to do is to split each of the word in the corpus into respective alphabets. So you see here, every word is divided or split into alphabets. Now we're going to find out the most frequently occurring pair, and this is a little function which will do that, and it will prepare the list of all pairs in the corpus. For example, I'm just printing the first five, so this is the first five pair here. And then we find out the pair which is happening or occurring the most number of times, and that would be this one here. So this is our first merge, and we're going to add that to our vocabulary here. So this is added to our vocabulary. Now we're going to also merge the pair into our corpus. So that for that we have this function here, and let's say you have a new word and you apply this function on a new word. It's identifying the first trained and is identifying this one as one token. Let's say we want to build a vocabulary of up to 50 as a size. Run through your vocabulary as a vocabulary size and looping through or iterating, finding out the most frequently occurring pair of alphabets. And you would be initially having 31 characters. Now you added 19 new merges. So this is your complete vocabulary after the training is over. Now, if you have a new sentence, the trained tokenizer can easily break this input sentence into individual tokens. This is how the byte pair encoding actually works. In the next video, we'll talk about a variation of the byte pair encoding called word piece tokenizer. So that was a quick demo on byte pair encoding with the theory and concept, and also a little implementation using Python and a GPT-2 auto tokenizer from Hugging Face library. Next, I'm going to talk about the word piece tokenizer in the next video. See you in the next session.